Well, welcome again, guys, to another linear algebra class. Well, we are in chapter 6. This is going to be the last section before I talk about vector spaces, and probably the last section that I'm going to actually test you guys over. Vector spaces might be on the final, but as a bonus problem or something like that. I don't know if I don't think I'm going to actually make it a regular test problem, just because it's a little bit more complicated, and I really don't like the way WebAssign does vector space stuff. So I might find a couple of problems with vector spaces and put it on there as bonus. I'm not gonna say that's gonna be for real. That's what I'm gonna do, but maybe I'll do that just because I want to see vector spaces represented some kind of way on the test or something like that. But today we're gonna do section 6.1 and 6.2, which is linear transformations. And we're not going to stay in there too long. We're just going to get kind of a idea about what it is, some examples, and then we're going to stop there. We're not going to go too deep. Okay, so section 6.1, 6.2, linear transformations. Okay. And a linear transformation, when it comes down to it, is a function. We haven't really talked about functions at all in linear algebra, right? We talked about matrix equations, and we did some matrix algebra, right? So we know how to multiply matrices together. We know how to add matrices. We know how to find the inverse of matrices, right? To be able to solve for a vector X or another matrix. We know how to do all those things. But we can also think about matrices in terms of kind of this functional relationship, and that's what we want to talk about now. And so linear transformations are just essentially functions that, and what we're doing is we're using kind of this matrix relationship when we deal with linear transformations, or with some of linear transformations. All right, so let's get started. All right, here we go. So topics for the day. We have definition of linear transformations. We're going to look at some examples of linear transformations. And then we're talking about some matrix transformations. Matrix transformations. So we have the definition of linear transformations, examples of linear transformations, and matrix transformations. All right, let me do something real quick here. I need to be able to see myself on the board here. Just make sure that I'm not in you guys' way. All right, so let's get started with the definition here. Definition. Let V and W be vector spaces. Again, you can think about vector spaces as just being Euclidean spaces for right now, from R2 to R3, R3 to R4, R3 to R3. We could also do vector spaces could also be like for functions and for polynomials and for complex numbers. Again, I'm going to talk about that a little later. But you can just think about vector spaces as being Euclidean spaces like R3, R4, R5, and so forth. And the function T from V to W is called a linear transformation of V into W if for any vectors U and V in capital V see any real scalar, okay, we have the following. The following are true. Okay, so let V and W be vector spaces. The function t from V to W is called a linear transformation of V into W. If for any vectors u, v, and v, capital V, as C any real scalar, the following are true. And these are the two things that need to be true. A, T of u plus V is equal to T of u plus T of V. So you can essentially do the transformation of u and v separately and add them together. That's the same thing as doing u plus v and then doing the transformation of that. And then B, the transformation, or T of C times U is equal to C times T of U. So essentially, if you take the transformation of U and multiply it times C, it's the same thing as taking C times U and then doing the transformation of that result. Right? So this is what we mean by a linear transformation. Now I have on here that V is called the domain of T. And W is called the codomain of T. And you probably have seen something like this before. Here, this is V, this is W, okay. And I have a function T. I have U and V here. Okay. And what is going to happen is T is going to take U and V into W, right? And my range of T is going to be like something right here. It's going to be inside of W. This is where T of U and T of V reside. Okay. So I have some space V with U and V in there. When I take the transformation of U and V by T, I'm going to get into W, and this is where T of U and T of V are going to reside, which is going to be the range of T. Now the range of T could be all of W, but it doesn't have to be all of W. The range of T could be much smaller than W. It could be all of W, or it could just be essentially only one point in W, right? And so that's kind of the interesting thing there. So, and a linear transformation, another definition here. T from V back to V is called a linear operator. Linear operator. Okay. The only difference between a linear operator and linear transformation is that linear operator goes from V back to itself. So a linear operator is a linear transformation. It's just a very special case where we take, so we go from R2 back to R2, R3 back to R3, R4 back to R4. A linear transformation doesn't have to do that. It can go from R2 to R3, R to R5, R6 to R7, those types of things, right? So linear transformation is much more general. Linear operator is very specific, it goes from V back to itself. All right. So some examples of linear transformations that you guys have seen that are not matrix examples. Okay. I like to do these two examples. We have derivatives. So if I take the derivative with respect to x of f plus g, right, where f and g are both functions of x, that's the same thing as the derivative of f plus the derivative of g. Okay, you guys remember that? also, what's the derivative of c times f, where c is a constant? Well, it's the same thing as c times the derivative of f. Right? So derivatives, or the operation of derivatives, is a linear transformation. So you can think of the derivative as being a function, right? So it's a function that takes functions back to functions, right? Another one that is not, it's like a matrix version of, what's the opposite of a derivative? Well, we have a integral, right? Integrals. Integral of f plus g dx. That's the same thing as integral of f dx. What's the integral of g? So, and then also, c times f, right? The integral of that is going to be the same thing as c times the integral of f. Right? So both of these guys are linear transformations that you can see that you guys have already dealt with in your math career. Right? However, we don't want to just stick there. We want to go to kind of more matrix-like things. Go back to Rn. So let's go there. Let's do a linear transformation that is a little bit easier for you guys. Here's an example. I have this one right here. I want to show that t from R2 to R2 is a linear transformation. If t, and here what I have, I'm going to write this a little bit differently from what I have in the notes. I'm going to write it this way: t of v1, v2 is equal to, here I'm going to have v1 plus 2v2, v1 minus 3v2. And also find t of 3, 4. We're going to actually find t of 3, 4 first, so we know how this works. Right? So I want to find t of 3, 4 first. I want to show that t is a linear transformation from R2 to R2. It's actually a linear operator, right? Because we go from R2 back to R2. Before we show that this is a linear transformation, because it is a much more in-depth process, we actually have to show those two things are true. Okay. Let's find t of 3, 4, right? Let's do that. Okay, very, very good. So let's do that. T of 3, 4, so if we'll do t of 3, 4. My v1 is 3, my v2 is 4. When I plug in, I get 3 plus 2 times 4. And here I have 3 minus 3 times 4. Well, what is 3 plus 2 times 4? Well, that's going to be, I think, that's 11. I think. And 3 minus 3 times 4, that's 3 minus 12. That is, what's that, negative 9? Okay. So if you guys remember from Calculus 3, right, when you guys dealt with functions of multiple variables or vector functions, right, both of those, this is the idea, right? Those are linear transformations that you saw there. Well, possibly. Some of those are linear transformations. But they act in a similar way. Not all functions in multivariable functions are linear transformations, but some of them are. So we have 11 and negative 9. Okay. So now I'm going to show that t of u plus v is equal to t of u plus t of v, and t of c times u is equal to c times t of u. So let's do that. I don't want to erase these guys. I'm going to erase everything else but those. To be able to show that this is a linear transformation, what we have to do is we have to show that the left side is always equal to the right side. Okay? We have to show that the left side is always equal to the right side. That's what we have to do. So let's kind of do that here. Let's say that U is equal to AB and B is equal to CD. Okay? That's what we have there. And so what I want to do is I want to show that T of U plus V is equal to T of U plus T of V. So if I do T, so U plus V, if I do it here, U plus V should be equal to A plus C, B plus D, right? Okay. You have to excuse my son yelling loudly about something right there. He probably doesn't hear it. His voice trailing. So let's do that here. So T of U plus V is what I want to do here. That's going to be T of A plus C, B plus D. Well, let's plug it. Plug it in, plug it in. We need to plug it into this formula, right? So essentially, V1 is my first coordinate. V1 is going to be A plus C here, plus 2 times V2, which is my second coordinate, which is B plus D. So I'm going to have A plus C plus 2 times B plus D. And let's look at the next one. If we look at the next component, right? So I have V1, which is going to be my first coordinate, minus 3 times V2, which is my second coordinate. So V1, which is going to be A plus C, minus 3 times V2, B plus D. And if I wanted to, I can multiply that out, right? 2B plus 2D. This is A plus C minus 3B minus 3D. Okay. Now, so that's the left side, right? This is the left side of this. What about the right side? Okay. Now, just like in trigonometry, if I wanted to, I can make the left side equal the right side. Or I could do the left side separately and the right side separately and see if they equal each other. That's what I'm going to do. I'm going to do the left side separately and the right side separately and see if they equal each other. So T of U plus T of V, T of AB plus T of, CD? Okay. Let's see if I can squeeze it down here. It's going to be tight, but it's going to be all right. So in this case, my A is V1, my B is V2. So if I just use that formula I have over there, I get A plus 2B, and this is going to be A minus 3B. Plus, here I have T of CD, so my C is going to be V1, and my D is going to be V2. So I get C plus 2D. Here I have C minus 3D. What happens when I add these two guys together? I get A. I'm going to write it the same way I have it here. I have A plus C, essentially, plus 2B plus 2D. Here I have A plus C minus 3B minus 3D. Are these guys the same? Are they equal? These guys are the same. So that means that T of U plus V is equal to T of U plus T of V. So the left side equals the right side. So A, the first one checks out. So this one here, the first property of linear transformations checks out. What about C of T of U? I want to show that that's equal to C times T of U. I'm going to use the same, so I have C times U. So C times U, I'm going to say that that is the same thing as what is that, CA and then CB. Okay. If we use the same U that we had over there. So let's do T of C of U. This is my left side. Right here. Right here. So it's going to be T of CA, CB. Guess what? So CA is my V1, CB is my V2, right, in this equation, for this function. So if we plug in, we get, what's that, CA plus 2CA? Nope, that's not right. 2A plus 2CB, there we go. And this is going to be CA minus 3CB. Here so that's the left side. What about the right side? Remember, we're trying to show that the left side equals the right side. Or you can continue working with this one to manipulate this into the right side. Either way is perfectly fine. I just like to do it this way because it's a little bit easier to understand what's going on. So left side, so I have C times TU. So I have C of T of AB. We have C times A plus 2B, A minus 3B. And then I multiply the C through, so I get CA plus 2CB, CA minus 3CB. And these, again, are the same. Okay? Between the left side and the right side. So this one here also checks out. So that means that T is a linear transformation. So therefore, T is a linear transformation. It's actually a linear operator, even more specific, but I wanted to show that it was a linear transformation. So if something is a linear transformation, the left, so these two properties have to hold. T of U plus V is equal to T of U plus T of V, and T of C